welcome everybody to the last session of this first day of the MAYA conference. So we will start with a talk by Roberta Tripodi. She's a PhD student at the University of Trieste, working on high-set quasars or QSOs and their galaxies. And we will learn today about high-resolution gas and dust on the first quasars.
Yes, thank you. First of all, I want to thank you, the organizer, for letting me present my ongoing research work about the study of the gas and dust emissions of these first quasars, with ALMA. The question is, why it is so important to study this peculiar object at high redshift? Objects that are supermassive black holes that accrete matter at the center of galaxies and eject a lot of energy. Because studying this peculiar object allows us to trace and analyze the history of formation of massive objects, because high redshift quasars are also thought to be the progenitors of the giant galaxies that we see now in rich environments through the observation. But how we want to study these objects? Basically, what I do in my PhD work is to analyze high redshift quasars, observation of high redshift quasars with ALMA, to study in details the emission of the gas and dust of the host galaxy, and also to derive their properties, and also to try to understand the relation that there is between the supermassive black hole at the center of the galaxy and the host galaxy itself. So going straight to the point, I want to present the main results of my PhD work. And for instance, I want to start with the analysis of a very high resolution, and in this case is 0.1 arcsecond observation of J2310 plus 1855. In particular, I want to focus on the C+ emissions that we detect for this quasar. What the high resolution observation allows us to do is first of all to spatially and spectrally resolve these emissions, and in this case we retrieve a size of about 2.6 times 1.9 kiloparsec squared. And from the moments map that you can see in the top right part of the panel, from the velocity map we can see this gradient in velocity that basically tells us that there is a rotating disk in this galaxy. And with this high resolution observation, we also can do a precise dynamical modeling with 3D Barolo, and the results of this modeling can be seen in the are overplotted as stars in the PV diagram on the bottom left, and we can retrieve the best estimate with a least certainty of the dynamical mass with this model, that is 3.8 times 10 to the 10 solar masses for this galaxy. And also what we can do with 3D Barolo is to study the profiles of the rotational velocity and the gas dispersion of J2310, and we see that the velocity rotation is almost flat around a value of 220 kilometers per second, and the velocity dispersion at the center is about 70 kilometers per second, and that's why we can also do the tumor parameter profile. That is very useful because this parameter can tell us if the disk is stable or unstable to the gravitational force at the center of the galaxy. In particular, for this quasar, if we focus on the scale between 0.6 and 1.4 kiloparsec from the center, we see that this parameter is around 1, 2, and so the disk is marginally stable because the limit of stability is 1. Parameters that are lower than 1 are unstable disk that form stars, basically. So what is amazing about this high resolution observation is that we found also molecular outflow associated with C+, and at high redshift there are very few cases of outflow in quasars. And as you can see in the PV diagram, this is taken basically along the direction of the shift of the two peaks of these wings, this outflow, the blue redshifted, the blue shifted part and the red shifted part. You can see that there are these emissions in the PV diagram that are not modeled by 3D Barolo, so are out of the dynamics of the disk, and so we can infer the mass outflow rate that is between 1,800 and 4,500 solar masses per year. And also we can derive the ratio between E dot and the volumetric luminosity. It is quite low if we compare this value with other values for molecular winds that, for example, are studied in the paper of Fiore 2017. And also from the talk of this morning, you can see that this outflow can be retrieved also in quasars at lower redshift, like the talk of Roman de Oliveira of morning that was really, really good. And then we can also, we can also, for the first time, resolve a water vapor disk at this high redshift. You can see the moments of this H2O emission line. And from this high resolution observation, we can also derive the size, the luminosity, and we can see from the velocity map that the gradient of this disk is consistent with the C+. And also, knowing the luminosity of H2O and the bolobertic luminosity of the quasar, we can see that our results, the red point in the lower right panel, is in very good agreement with the correlation that Young 2013 found for this relation, and also with the other mid and high redshift quasars that were observed during the last few years. And so from this plot, what we can learn is that the H2O line basically is mainly excited by the infrared pumping mechanism of the dust reprocessed radiation field in the host interstellar medium of the galaxy. Then what we want to do is to extend this analysis to a larger sample of high redshift quasars to see the average behavior of these objects. And the sample was drawn from the hyperluminous quasars at the epoch of reionization with two fundamental selection criteria. That is the mass of supermassive black hole and the fact that these quasars are also in the XMM Newton heritage program. And from my point of view, I want to investigate the nuclear and the host ISM, but there are also other objectives for this Hyperion survey that I list here in the slides. So what we want to compare for the beginning is the size of the dust component and the gas component, also comparing our sample that is listed in the legend in the left panel with other sample of lower redshift quasar, for example, from D'Amato et al. 2020. What we can see is that the dust size has an increasing behavior with redshift and is also greater than the dense molecular gas in high redshift quasars. And this molecular gas size is retrieved from the C+ for J2310, but for the other quasar we study the carbon monoxide transition 6 to 5. And what I want to stress also is that the little uncertainty that we have on the determination of the size is the direct consequence of the high resolution of the observation that we study. Then we moved our analysis to the dust spectral energy distribution. We adopted the method that is the modified black body well described in the paper of Carnani 2019. I report only the main equations to model the function to fit the observation point. And we have three parameters: the dust temperature, dust mass, and beta. And it is important to well constrain this data because we can retrieve the star formation rate of the galaxy. And it is important because we want to compare, we can compare the evolution of the supermassive black hole with the evolution of its host galaxy. For example, you can see the plot on the right. If we have a good estimate of the black hole accretion rate, the black hole mass, the dynamical mass, the star formation rate, we can distinguish between different regimes. There are the black hole adjustment, symbiotic growth, and black hole dominance that characterize the supermassive black hole in relation with its host galaxy. So I present here our best case, that is SDSS J2310, because it has a very accurate sampling of the distribution made of ALMA data and also airshell data at lower wavelength, these points here. And because of this accurate sampling, we can see that we derive a precise determination of all the free fitting parameters. And for instance, we retrieve a dust temperature of 70 Kelvin, a dust mass of the order of 10 to the 8 solar masses. So we can infer a formation rate that is 1,400 solar masses per year. That is a little bit smaller than the one reported by Xiao 2019, actually. But what I want to stress in this slide is that the essentiality, the essentiality of having ALMA band 8 and 9 point at high frequency, because they are necessary to tightly constrain the dust temperature of the quasars analyzed. So, thank you. So for the big sample, we have that the dust temperature and dust mass are of the order of 70 Kelvin in average and 10 to the 8 solar masses. And we have that the high accuracy of the data point are due to having a high frequency point for the dust mass and probing well the most leading part of the distribution for the dust mass. And then we can compute also the gas-to-dust ratio. That is very important because in many articles in the literature, it's a quantity that is assumed. Instead, here we can derive it from our analysis, and we derive that a gas-to-dust ratio that is in the range between 13 and 150, and the points that have a gas-to-dust ratio of the order of 100 are the most accurate, are the points that have the most accurate spectral energy distribution, actually. And we can see also that from the plot on the right, that it also is quite independent of redshift, because the range in which it varies basically the same at lower and higher redshift, comparing with the quasar of D'Amato 2020 and Kalura 2014. So now, summarizing a little bit and drawing the conclusions, I showed you the study we are doing about high redshift quasars, studying the gas and dust emission with high resolution ALMA observation, in particular focusing also on the results of the quasar J2310, because it has very nice characteristics. In particular, we can resolve the rotation curves, and this allows us to have a precise dynamical modeling to retrieve the best estimate for the dynamical mass. We can also discover a molecular outflow in these quasars, and so we can retrieve derive the mass outflow rate for the quasars, and also a weirdly low ratio between E dot and bolometric luminosity. For the first time, we were able also, thanks to ALMA, to spatially resolve the water vapor disk in these quasars, and so we can state that this H2O line is excited by the dust represented star formation rate in the interstellar media of the host galaxy. And then talking about the properties of the whole sample of high redshift quasars, we can see that I showed you that the dust size is overall greater than the gas size in this sample, and also that the gas-to-dust ratio is of the order of 30-150, with only a slight variation with redshift. But what is essential here to, for example, study properly the spectral energy distribution of the dust of these quasars, to have high redshift point in band 8 and 9 of ALMA, to tightly constrain the dust temperature, and so to retrieve a reliable estimate of the star formation rate. Okay, so thank you.
Thanks a lot for the talk. So to me, it's very impressive that you have this band 8, 9 observations that you can really fit the acidity peak. So was it very much time what you had to spend at these bands to do the observations, or is it, I don't know if it's a long integration or a short integration?
For J2310 is a longer integration time, because it's like 4 hours of integration to retrieve this high resolution data. But basically, for the spectral energy distribution of the dust, I mixed up all the data on the archive. So we have also different resolution for each observation. So also 1 hour or 2 hour observation is sufficient to probe quite well the spectral energy distribution.
Okay, I see. Yeah, thanks. I think there are some questions in the chat.
Yeah,
I can read them, or
yes,
Marcella, you want to? Yeah, okay.
Yeah, nice talk. And there is a question, maybe I just missed this info, but what is the redshift of the quasars J2310?
Oh, sorry. If I didn't tell you, is 6003. So basically redshift 6.
And I have a question myself. And what about the rest of the sample? So you say you have a sample of high redshift quasars, and it's how did you select it, and what was the range of redshift that you cover?
So the range of redshift that I covered is between 5.7 and 6.1. So basically redshift 6, and I select them because they are drawn from the Hyperion sample. I don't know if you can see. Okay. Oh no, God. Okay. No, okay, here. You can see my slides, right?
Yes.
Okay, so they are drawn from the Hyperion sample. So I select them because they are redshift basically 6 from 5.7, and also they have a supermassive black hole mass greater than 10 to the 9 solar masses. Yeah, these are the main criteria of selection.
I have another question in case there are no others in the chat waiting.
No other questions at the moment.
Okay, so while people think. So I had a couple of questions. One, it's very basic, but for an outsider of all this AGN and so on. So the energy content in the outflow was very low, right? So in the one that you reported. So, but if I understand you correctly, it's because this is one of the very early QSOs. And then if we would come to closer redshifts, so would the energy of the outflows increase, or do you expect to not be relevant at all? Or?
Actually, the point is that in the paper of Fiore 2017, there are also high redshift quasars. They show a high value of this ratio. So it's not necessary that high redshift has to be a low value of, in fact, the point is that this ratio tells us if the outflow is energy conserving or not. So if this ratio is high, the outflow is very energy conserving. Otherwise, if it is low, it's not energy conserving, maybe it's momentum driven or something like this. But we have still to discuss this point because it's a bit strange. So yeah.
Okay, thank you.
There is another question, very quickly, related to your difference between the gas versus dust size. And the comment is that the sub-millimeter galaxies typically found to have larger gas size. And they are asking, what is your comment about the difference with respect of this?
Well, sub-millimeter galaxies are different are different from quasars. Actually, have also different properties. So it's not be too strange if the gas size and dust size has different behavior in these different objects. But in particular, so in superregard, they have larger gas size, and it also depends on the redshift of this object, because you, if I can wait, okay. Okay, actually at lower redshift, the gas size is greater than the dust size. So we have to know at what redshift we are talking about, basically, and also it depends also on what kind of gas you are looking at, because I'm looking at higher transition of the carbon monoxide that trace the most inner part of the gas. Maybe looking at different transition of the CO, I can find that a gas size that is basically comparable to the dust size. So there are many differences here.
Okay, so so there is one more question, I think. Should we maybe put it to the Slack channel, because
yes,
we are over time? So
okay.
all the questions will be moved there. So Sangji, so you were asking this, so we can follow that on the Slack channel. Thanks a lot for the talk.